Good day, everyone. Today we are going to take a look at our notes on section 6.1, taking a look at the ideas of impulse and momentum. So first of all, let's talk about what the term momentum means. Momentum is an object's desire to keep moving. We often use the term momentum fairly colloquially. Once you get going on something, we say you've got momentum to continue it, to carry forward. It's kind of the idea that once you get us started on a project or get started on work, you generally can keep that carrying forward. Well, it's the same idea here. Momentum is just the term describing the inertia of an object that is in motion. We calculate momentum by multiplying the mass of an object by the velocity. So mathematically, that's really all we have to worry about. We just have to look at the quantities of mass and velocity. They get multiplied together. Now, because velocity is a vector, momentum is a vector as well. It's always going to match the direction of velocity. So that's an important thing to remember. And unlike things like kinetic energy, mass and velocity have equal impacts on the momentum of an object. A faster object will always have more momentum, and a larger object will always have momentum, as long as it's moving. Regardless of any size, the object will always have zero momentum if its velocity is zero. And the unit for momentum is kilogram meters per second. We just multiply the two together, and that's it. This doesn't have any shorthand, and the International System of Units still won't recognize my petition to call it the Hatzberger, so we'll just stick with calling it the kilometer meter per second. Now, impulse is a little bit different, and it's a little bit more complicated than momentum on its own. Because impulse is talking about the change in the momentum. So there's a couple ways we can calculate the impulse. We can calculate it by mathematically subtracting the final momentum from the initial momentum. That's the first one. We can also look at the force applied and multiply it by how long that force is applied for. That's another way that we can look at the impulse. So if we put these two equations together, we get this one right here. Force times time equals the change in momentum. Now, that's generally going to be how we see impulse in one of these three equations. And so also knowing P final and P initial, we can find final velocity or initial velocity by substituting mv in for whichever momentum we're looking for. Now, generally, if the impulse is positive, we see an increase in the momentum. If the impulse is negative, we see a decrease in the momentum. It's important to recognize that mass and time are not vectors. Mathematically, they should always come out as a positive. Anything else can come out when we deal with a negative vector. And so the reason time gets factored in is for this reason right here. If you push on something for only a brief moment, you have a very small impact on its change in momentum. If you push for a long time, we see a much larger change. All right, so let's do some calculations. Calculate the momentum of a 30,000 gram box that covers 10 meters in 2 seconds. So what do we have? We have mass, 30,000 grams, 1,000 grams per kilogram. That is a 30 kilogram mass. It covers 10 meters in a time of 2 seconds. So bringing these together, we get our velocity, distance over time, 5 meters per second. And to calculate our momentum, we are just going to multiply our mass times our velocity. 30 kilograms times 5 meters per second, 150 kilogram meters per second. Example 2. Calculate the velocity of a 250 kilogram car that has 4,500 kilogram meters per second of momentum. Now notice here, momentum is mass times velocity. We have to get the velocity here. So we're going to divide, not by the velocity, we're going to divide both sides by the mass. And this gives us velocity on its own. 4,500 kilogram meters per second divided by the mass of 250 kilograms. The units cancel out, nice and neat. 4,500 divided by 250 comes out nicely to 18 meters per second. So now we're going to take a look at an impulse problem. Determine the impulse of a 400 Newton force that accelerates a 2 kilogram mass for 20 seconds. We've got our force, we've got our mass, and we've got the time. So, if we want to get the impulse, it's either the change in momentum or force times time. Well, we have force and time, so we're going to ignore the mass for the time being. We don't need the mass to calculate the impulse in this case. It's just going to be 400 newtons times 20 seconds. And that's going to give us 8,000 Newton seconds. Example 4. Determine the final velocity of a 300 kilogram car that accelerates from 1.5 meters per second due to a force of 260 newtons over the course of 34 seconds. All right, let's put this together. Start with the givens. Now notice that I'm using the initial velocity here because this initial velocity of 1.5 meters per second is where the car starts. We're asked to determine the final velocity. So we're going to get that at the very end. The force is 260 newtons. and the time is 34 seconds. Now for this one, we're going to have to use that combined equation of impulse, where force times time is equal to final momentum minus the initial momentum. Now, the initial momentum, we're going to have to calculate that first. That's mass times the initial velocity, both of which we have. 300 kilograms times 1.5 meters per second. That's 450 kilogram meters per second. So the force is 260 newtons. The time is 34 seconds. We are looking for final momentum, and we're subtracting that 450 we had before. So going to our calculator, 260 times 34 is 8,840 Newton seconds. Now, you might be taking a look at this and saying, hey, wait a minute, Mr. Hatz. Kilogram meters per second and Newton seconds are not the same unit. And you would be correct. Theoretical student that I'm making up in this virtual quarantine who can't actually ask me a question in person. They are not the same unit, or at least they don't appear to be the same unit. Remember that the Newton is a shorthand unit. The Newton stands for kilogram meters per second squared. And that's getting multiplied by seconds. And when those seconds cancel out, they actually turn out to be the same unit, kilogram meters per second. So we are going to add 450 newtons to both sides to get the final momentum. 9,290 kilogram meters per second. And now the last step to get the final velocity just like in example 2, we're going to divide this by 300 kilograms, the mass of the system. And it'll come out to be 31 meters per second.